This next one's not too much different. It's all point loads. We'll get to some examples that also have couple moments or pure moments as well in the next example. Just a little bit more complicated this time because we've got some inclined loads, and so therefore we're definitely going to get a reaction in the x direction from here somewhere. So just thinking ahead to what I'm going to try and do. So I've already drawn the free body diagram here. And then we are going to, so I've drawn the object by itself with all the little bits and bobs removed, just so it's the object itself. In reality, you maybe could include this little block and this little eyelet in your free body diagram, but just quicker to draw it without them. Then so we've done that. The next step will be to try and figure out, look at the types of supports and figure out what kind of reactions can you get from them. This is a rocker. And so for a rocker, it's like a spherical object on a smooth surface, and so it can only give a reaction. It can only give a reaction perpendicular to the surface, and so therefore it's going to give us some reaction that can't give us anything in the y direction. We'll just try and be consistent with our labeling, so we'll call that RAY. The other thing I've done, just as I was drawing this, I've just drawn these to approximately the right scale. It's not exact, just approximate, and it just makes sure that you're keeping your eye on, you're looking at it kind of graphically and making sure your answer makes sense. Whether RA is the right size, don't know yet. Other end, this is showing a pinned connection, so it can't have a concentrated moment reaction, so it can't have a moment reaction, but it can have both an X and Y reaction. And I'm thinking to myself, it doesn't actually matter which direction you draw. This one, obviously, this reaction is going to be upwards because all of these forces have a downwards component. If you were to figure out the resultant of those, it would also have a downwards component, but we're looking at the reaction to that. And so it must be in the upwards direction to stop this resultant pulling this beam down. It must have a reaction in the upwards direction. And we've really only got one component in the x direction. This 600 Newton is going to have a component in the positive x direction. So this other reaction, we'll call this RB. Is that B? It is. And then we must also have, interesting, they have made this a little bit more complicated. And so these are in the middle. So I'm just looking, they've given us this dimension. And so therefore, we're just going to have to be careful about the position of these and take account of the lever arm. These ones won't matter, but the lever arm of this has got two components. It's got a lever arm to the X component, because that's 0.2 millimeters, and then it'll also have the Y component here. It'll have a lever arm of 2 meters. They wouldn't have given us that. What they sometimes say in a question is ignore the thickness of the beam, but in this case, obviously, they don't want us to ignore the thickness of the beam. They've given us that 0.2 meters, and so it'd be better to draw those actually at the center of the beam, so we don't forget that. It's there, and similarly, this one must be to the center of the beam here, and we're also going to have a reaction. Why I was talking about that is we've got one X component going this way. So this, could even draw those on now. So these are not acting at the same time. I'm just drawing the components of this 600 newtons. The point of application has been drawn at the nose. So the point of application of the components must be at the same place. And so we're going to get an X component, and we'll call that F1X. Just going to shuffle this out the way a little bit. And we're also going to have a Y component. So that's going to be F1Y down the way. And we can always use, now I still need to add in a little, and it's being applied at the top of the beam, like so. So that's F1Y. What else do we need? We need to know we know that this here is 45 degrees. I'm going to do that in blue because it belongs to the original force. And so we could replace that 600 Newton force with these components. We wouldn't change anything. I'll just draw this one dotted so that I don't get confused and take my lever arm to that. The point of application is the same as the original force. It's 45 degrees F1X. Getting a bit messy, but it'll be okay. So we'll draw those on. Okay, so we've got one F1X, so we've got one component of X in this direction. So the reaction to that, the thing that's making this beam stable and not slide to the right, is the fact that there must be a balancing reaction at this side. So really, when we're checking overall stability, we're checking sliding in both directions, x direction, y direction, and then we're also checking total moment. So that's where you're getting the sum fx equals 0, sum fy equals 0, and sum of the moments is equal to 0 for rigid body equilibrium, where all the forces don't cross at one point. If they did cross at one point, you'd lose all your moments because there's no lever arm. Therefore, you just need sum of the fx components equals 0, sum of the fy components equals 0. Right, so we're about ready to get started now. What I would probably do first, let me just have a think about what I'd do first. Let's start with the forces. And so we'll figure out what the reactions are. Oh, I haven't labelled these, so that would be, I have a little bit, but not really. So we've got an RBX is here, and why do you keep doing that? RBY, it's going upwards, and RBX, B because it's at point B, X because it's in the X direction. Cool. So we already said we only got one X component, so let's start with that, of the applied forces. So we can start with sum of the X components must be equal to 0. That implies that F1x, so it's in the positive direction, minus RBX because it's in the negative direction, so it's going this way, must be equal to 0. And you could see it just by looking at it. You don't even really need to write down the equation, but F1x, as long as you're drawing it in the right direction, must be equal to RBX. Would have been better if I'd done those the other way around because we're trying to find RBX. So let me just do that. So therefore, RBX equals F1x equals 600 times, so what have we got here? We've got the hypotenuse, it's the adjacent, that's the angle here, and so cos 45. Get the calculator. 600 times cos 45 equals 424.3. 424.3 newtons. So we found one reaction now. We found this reaction. That's its value. Let me just check that makes sense. All looks sensible to me. And we're just remembering that RBX, it's a little tricky. Like you could think about this as being the magnitude of that, or you could think of it as being like this RBX, we're trying to explain the whole vector. So we're going to give the magnitude and the direction. And so what you can do is you can just draw that little arrow like so. So it's 424.3 newtons that way. And in an exam, I would accept that answer. It's just 424.3 newtons that way. But you might also want to answer, you might want to draw a set of axes, and we'll just, for these types of problems, we'll just always use them this way. So y is positive, bottom going from the bottom to the top, and x is positive going from the left to the right. It just gets a bit too confusing in these problems if you veer from that, especially if you're trying to mark it. And so we could also write that as, if you're trying to say, explain the magnitude and its direction all in once, you could say that's minus 424.3 newtons with respect to, so WRT with respect to axis shown. I'm not going to write that down. Okay. I'm not sure what's best to do at this stage. Let me just work through the rest and we'll decide whether it would be better just to leave it like this for now. I think it probably would be, so that you're just showing the direction rather than trying to take account of whether it's negative or positive. You just have to keep looking at things as you go along. So let's just put the arrow for now and see what happens. Okay, now we can also take the sum of the y components must also be equal to 0. So what have we got there? So let's not try and miss any. So we know that RA plus, because it's positive, it's going in the positive direction, RA plus we should really have called that RAY. So let me just do that, RAY plus RBY Then, what have we got in the negative direction? It told us to ignore the weight of the beam, so we didn't have to worry about that. But then we've got minus F1y minus 100 newtons. So just going from left to right, and I'm just making sure I don't count this twice. Okay, again, this is why I dot these ones, just to make sure I don't count it twice. So F1y is down that way. We've got 100 newtons downwards as well, so that's minus 100. And I don't know why there would be a 200 newtons going up the way, just because I'm a bit stupid. This to work. We've also got 200 newtons applied right on the support. 200 newtons right on the support there, and that's downwards, so again it's minus 200 minus 200 newtons must be equal to 0, because all of your y components must add up to 0, so the applied loads and the reactions need to cancel out. Don't know why I put the units in. Right, so then what we think, we don't actually know RAY and RBY at this stage, so it might have been more sensible to do the moment first, because what I could have done is I could find the moment about the point B, probably just put those on so people can see what I'm doing. That's A and this is point B, and it's the little point in the middle. So it might have been good, but probably wouldn't have been, because we're going to have an F1x in this direction as well. So it's going to have a moment about both of those points, because we're allowing for the thickness of the beam in this one. And just to be clear, what I should probably do, and what I should have done in the original drawing, I'll just put these on. I'll fast forward through this, is I'll just put on these dimensions. Okay, so I've got all the dimensions on now. What was I talking about? I was trying to think, would it be better to do the moment first? Because I was thinking I would eliminate these two forces because they don't have a moment about that point, because they don't have a lever arm. And that would have maybe left me with one force that I don't know. And I can calculate F1x. We've done it above here. So that is actually F1x. Yep. And so that might have been a better move to do that first. But anyway, we've started this one now, so let's push on with that. And this is what I'm trying to get to with these problems. Sometimes you just have to look at the three equations, see where they lead you, and maybe try and solve all as much as possible. And you might get left with a couple of variables, so you can't solve it. Then you do the next one, and that'll give you enough information to finish off the whole question. So let's push on with this one now. So we've got that. What do we know? We can figure out F1y. So RAY plus RBY minus, we can calculate F1y, it's equal to 600 sine 45. Okay, so this is my F1y, imagine moving it nose to tail over here, and so we can just do 600 sine 45, that's not a problem. Minus 200 is equal to 0, that was just that load that's on the point there. And so let's just calculate 600 sine 45. Sine 45 equals 424 point. Of course it is. Sometimes you can too busy thinking about what I should be telling you to think about the maths. So of course it's the same as this, because this is 45 degrees. So that must be 45 degrees as well, because they add up to 180. So you'd have 45 plus 45, 90 plus another 90 is 180. Therefore, these two angles are the same. Therefore, this is isosceles. Therefore, these two forces must be the same. Okay, that's where I'm going with that. So RBY minus 424.3 minus 200 is equal to 0. And then we've got RAY plus RBY is equal to 624.3 newtons. Coolio. Now we can't solve that. One equation, two variables, can't solve that at the moment. But we've got one more weapon in our arsenal, which is the fact that for static equilibrium of rigid bodies, we must also have the sum of the moments is equal to 0. So we're going to have to look through this and find all the moments. Let's have a look. So just keep in mind, I've said it a couple of times now, I'm drawing all of this on the same diagram. One of the reasons I do it in different colours is we don't want to count this twice. So we've got the 600, but I've split that up into its components, so I don't want to count that again. But anyway, let's work through this. So all of that must be equal to 0. Therefore, now we have to think about where we're going to take the moment about, and we take it so that we eliminate as many unknowns as possible. So we don't know RBY. We do actually know RBX. We've calculated that. So we could take, you could use this point. What would that give us? That would give us RBY on its own, I think. So it doesn't really matter actually for this one. You could take either of these points and I think it would give you the information you need. So say I take these ones. These two have no moment. This one has a big moment. It's got this force times, there's the lever arm, the perpendicular distance of the line of action to the point you're thinking about. We know these. It's going to have a moment, a small one, because the F1x, its perpendicular distance is only 0.2. And then we've got F1y, it's got a moment as well. This one here has a moment. And so we calculate all those, this one doesn't. So therefore, we could figure out the answer. But I'm just thinking now, okay, B has 3 forces going to it. So I can eliminate all 3 of those if I take that point. Whereas if I take this point here, there's only 1 force I'm eliminating if I use that moment. All of these other ones all have moments. So it's going to make my calculation easier if I use B, get rid of all these because they've all got 0 moment because they all go through that point. And then I only have to calculate the other ones. So I'll do that now. So each case, I'm just going to look at the moment, find its lever arm, and we'll figure out the answer. So I'll just fast forward through this bit as well. So we got here. So I've worked through that. Let's just have a look at what was going on here. And so I've just been careful. So I've taken the moments about this point. I've just explained that here. So you've taken this point to eliminate as many forces as possible because they all have 0 moment because they all go through the point B. So I've taken moments about that point. Then I've just gone through all the forces we've got here and checked what their moments are about that point. So RAY has got a lever arm of 7 and it's going in a clockwise direction. So it's negative. Now you might have noticed in the fast forwarded calcs, I actually got that wrong to start with. So always I'm checking back to make sure it makes sense. If I've drawn these arrows on in the right direction, I should be getting all positives for the magnitudes if I've drawn them in the right direction. So if you think of these as being the magnitude of that vector, you've drawn the vector in the right direction and you've used that direction to get your moment. Then it should be the case if you've got them in the right direction, you should never get a negative result for your magnitude. The only time you get a negative result for your magnitude was if you'd drawn this in the wrong direction. You'd use that for the direction of your moment, that wrong direction, and then it would come out negative and you'd realize, oh, I need to change the direction of that to the other direction. Okay, so it's a little confusing. Like you can think of these as the whole vector in that direction, in which case you use your positives and negatives to show the direction, or you can think of these as just being the magnitude. Now that's what I'm doing in this case. I'm thinking of these as the magnitude. They're all positive, and then I'm using the arrow to show the direction. And therefore, if I've got that direction right, I use that direction to decide whether my moment's positive or negative. All of these magnitudes should come out positive. If they're negative, then I'll go back and check, could that be the other way around? In this case, it can't be. I know that those are the right directions for these just by looking at it. And so then I rethought, oh, I forgot that this one I put it down as positive, but actually it's going clockwise with this direction. Therefore, I need to make sure I'm writing down that moment as negative. Okay, and then I've just figured out, so we've got this force here has a moment, this force here has a moment, just being careful whether they're clockwise or anti-clockwise about the point B. I'm doing everything about the point B, and I've worked through and got my answer there. And then I've written out the, so then what did I do? So then I took that answer, so I've called it 2, so I can explain to people what I'm doing. That's equation 2. I've substituted that into this equation where we got stuck because we had 2 components or 2 variables or 2 unknowns in one equation. But now I know one of those unknowns, so I'm left with only one unknown, so I can now solve this one. And so I've solved that and got that answer. So what I'll do finally, and that's the moment of truth, is I'm just going to go through this again, and I'm going to find the moments about A, and if I've got everything correct, that moment about A should also be 0. The moment about any point should be 0 if we've got static equilibrium. So because this is so far away now, I'm just going to grab it and copy it down here. And this is all a bit of a check. O-U-Y. There we go. Try not to swear at OneNote in a lecture. I might turn it all into grey. This is all a check now. So we'll turn that all into grey. And then I'll just do a quick check calc for the moments about A. So see you on the other side. Okay, so I worked through that check. What I discovered at the end of this was I was getting 700 here instead of I should be getting something near 0. So you see it's not exactly 0, but I was working with numbers like, 404.7 times 7. Okay, so you can imagine if I've rounded to this decimal point, that could be 0.1 wrong, if you know what I mean, roughly. And so if you times that now by 7, it could be 0.7 wrong. Okay, so this is rounded to the nearest 0.1, 3 significant figures. So you could think, well, it might be an error of plus or minus 0.1. By the time you multiply that by 7, it could be plus or minus 0.7. And so this error is well within the rounding error of this calculation. But what I was getting originally wasn't. It was 700 out. And because it was 700, I was thinking, well, it might be to do with this 7. I might be 100 out somewhere. And so I looked back at my calcs, and what I found was I'd lost that 100 at one point. So I'd worked through here. I'd forgotten to write the 100 here. Okay, so I didn't get it right first time. And to be honest, I'm getting more careless as I'm getting older. When I used to do my maths, I used to be quite accurate and didn't get things wrong too much. But as I get older, it's my sob story. As I get older, I tend to make more stupid errors like that because I'm thinking about other things while I'm doing it rather than concentrating. But that's why you do checks as an engineer. It's really important you get the right answers. Therefore, it's worth taking the time to do a quick check. And the way you do checks for these ones is we've used one of these points with that sum of the moments equals 0, but you could use any point. You could use any point at all, and the sum of the moments should be 0. So I've just taken that other point. I've calculated all the moment as a result of all those forces around that point, and checking it should go to 0 if we're going to have static equilibrium. And it didn't, so look back, find the error, fix it all, and it should be right now. Okay, and this is the first time, when I do these, this is the first time I've looked at these problems, and so that's why sometimes there's errors in them, and I would be probably better for me to go, well, probably not actually. I was going to say it would be better for me to go through them and do it all right, but actually probably not, because it's quite good for you to see how you approach these problems, realize that I don't exactly know what I'm doing to start with. I'm just trying some different values and see what works and what doesn't, substitute things back in. And then I'm checking my answer at the end to make sure I get the right answer. Okay, that's that one. Let's move on to the next one.